All right, hello everyone. So today we are going to be going over function calls and return statements. So previously we added support for function declarations into our language. Specifically, we added code to generate one single function, our main function, and now let's put it to use. So we would like to define multiple functions. We'd like to call functions. We'd like to return values from those called functions. And then, excuse me, we would like to pass an argument to our functions. For the moment, it will be temporarily unusable, but we will fix that in the future. So let's cover the LLVM. This is mostly a recap. We've generated code like this, all of it before, but now we're just generalizing it. So we've got our defined statements. We give it a return type, we give it a name. The @ symbol means that it's a global identifier. We've got the same thing for main here. For returning values from functions, we've got ret. We give it a return type, and then we can either give it a constant or a register. Or we could give it void like this, where it's got nothing after the type. And then when we want to call functions, we say call. We give it the return type of that function. We give it a list of types of the parameters of the function. We give it the function name, and then we give it the parameters themselves. So, starting off, when we are declaring multiple functions, we've actually basically accomplished this completely. In our previous lecture, thanks to the generality of the code updates that we made. There is one small change. So I've defined this translate reinit function. So at the beginning of every function definition, we want to do a couple things. We want to restart our virtual register number count. And the reason for this is, although you can use any string for your virtual register names, if you do choose to number them like we're doing, Clang will enforce that numbering from 1 to however many you go to linearly. So you can't skip around, you can't go from 1 to 4, you can't start off at a different number. So if we generate code that uses registers 1 through 10 in one function, and we try to start on register 11 in the next function, Clang is going to throw an issue there. So we want to reset that at the beginning of every function definition. For free registers, realistically, we should never be ending up with any extra free registers. However, in the case that does occur, we want to be safe and just empty out our list, because you can't reuse registers that are declared in one function and another since they're local. And then you've got your list of loaded registers. So if I load registers 1, 3, and 7 in function Fred, and then down in main I try to use that virtual register 7, if I don't clear the loaded registers, there's a good chance that I'll run into an issue where I'm trying to use a pointer to a function, or a pointer to a number, rather than the actual number itself, because if you haven't cleared that loaded registers list, it's going to think that register 7 is already loaded, even though it isn't. So we can see that translate reinit gets called right before the function declaration call, and right before the AST or the LLVM generation. So that's very nifty. Now for calling functions, so we've decided that we are only going to allow one argument right now, and it's not going to be able to be used inside of the function. Eventually we will work on fixing this and passing however many arguments we want and letting them be used in the function itself. But right now we just want to give a precursor to that and see what it's about. So we run into an interesting problem when we're parsing function calls, and that problem is that function names are identifiers just like variable names are. Fred is a valid function name, but it's also a valid variable name. So everywhere we were dealing with parsing or checking variable names earlier, specifically declarations and assignments and R values, we now have to check ahead for a left parenthesis to see if we're actually looking at a function call. And we're going to do a kind of roundabout checking for left parenthesis, and I think actually by the time I had finished this, I had changed most of those checks to just type checking of the global symbol table. But we'll see how that gets implemented in a second. But we just want to make sure that whenever we're scanning in an identifier, we want to know whether or not we're looking at a function call or a variable name, because the distinction is obviously very important. So function calls are actually expressions. They are not statements. You can have a function call in an R value, or you could just have an entire statement that is a function call. And so I've defined this function call expression inside of the expression parsing file. So the way it works is by the time we've called function call expression, we assume that we've already scanned in an identifier. And so it should be stored in the global scanner current token. However, there's sometimes when the control flow will lend itself to scanning in another token earlier. And in those cases, we've got the option to override the function name that we're expecting to see. So that's just some type checking right here. And then right here is where, if we haven't set an override, then we're just going to call that string that we're going to be using. We're going to assign the value of whatever's in the current token to it. And we're going to pass that, whatever that is, into the global symbol table. We're going to get an identifier or a symbol table entry out of it. Obviously, if it's not declared, we should throw an issue, an error. We should not be trying to call undeclared functions. That's bad behavior. And then what if the identifier is not related to a function? Then you've tried to call a function, but the identifier is a number instead of a function. So we should not allow that to happen. After that, we are going to match a left parenthesis. We are going to parse a binary expression that we are going to use as our single argument for now. Again, in the future, we're going to change that, but just looking ahead at what the possibilities are right now. We are going to match a right parenthesis, and then we are going to construct an AST node. We are going to give it the function call type, new token type. We are going to give it the identifier name, or the function name of the function that we're calling. And then we are going to give it our single argument as as the left child of the AST node. And so let's look around to see where a function call expression got called. So there's two places. We are not going to look at the assignment statement right now because this should be an error. I'll push a fix for that, but this should be an error. In parse terminal node, this is the big change where we need to check for function calls. So previously, parse terminal node, we were using it to check for integer literals, and then we would specifically look for variable name identifiers. Now we are adding a case for whether or not the contents of this global symbol table entry are a function. If it is, we want to match an identifier, and then we are going to call function call expression. So nothing too crazy there. I think that makes fairly good sense. And then parsing return statements. This one is very straightforward. We are just going to match a return token. We are going to get the global symbol table entry of the current function. So we don't have to do this right here, but it does make something a little easier that I'll go over in a second. But just very quickly, the current function name, that's a new variable inside of Global Scanner that I've assigned whenever we start a function declaration. So the Global Scanner will just hold on to that specifically for parsing return statements. If we can't find anything using the current function name, then we'll say we've lost track of that function. So that's not good. And the reason we did this at all is to check the expected return type of the function. So if we have a void function, we should not even try to parse a return value. We should just have a return statement that doesn't have anything after it. It's just return semicolon. That's all we want, right? So if we do have a void function, then we are immediately, as soon as we match return, we are immediately going to return an AST node with the return type, and we're going to give it the function name for an extra layer of type checking in the code generator. Otherwise, we will be able to parse a binary expression to use as the argument to our return statement. So that's return statements for you. The reason I'm doing all of this extra type checking that I really shouldn't need to, and we'll see it more in the code generation stage, is because I originally wrote this code in C, and programmers writing C are susceptible to making memory mistakes. You might overwrite memory that you didn't want to, or you might forget to set memory that you wanted to, and the more checks you have for that, the better. And C is a fast enough language that you don't really lose any time checking the expected types of your functions and whatnot. So I added lots and lots and lots of type checks everywhere to make sure that none of my code was doing anything that it shouldn't, and if it was going to do something that it shouldn't, then it was at least going to tell me explicitly, hey, here's a warning, you shouldn't, this shouldn't be happening. So that's return statement. We can see it gets called here in the big parse statement loop. Just a basic extension of everything that we've already looked at here. And so now let's work backwards. Let's look at the return statement code generation. So do some type checking to make my linter happy, and then we are just going to call this new LVM return function. Oh, that's not what I wanted. And we are going to pass in left VR, which is whatever possible return value that we have. It could be none, or LVM value type.none if we have a function with no return value. But let's take a look at that. So this is our LVM return function. So what we're going to do is we've got this function name that the return statement is a part of. We get its global symbol table entry. If there's no entry, we're trying to return for some function that isn't declared, which doesn't make any sense, but again, we want to make our linter happy. And we want to make sure that whatever identifier we're dealing with is a function. That's another thing that could go wrong. And the next thing is that we want to generate two different kinds of statements depending on whether or not we are a void function or not. So if we are a void function, it makes it really easy. We can just print out ret void, and we're all done. Otherwise, we want to ensure that whatever we're trying to return is loaded. We don't want to try and return any unloaded, stack pointer stuff. And then we are going to write ret. We're going to give it the number type, and then we're going to give it the virtual register. So nothing crazy there. That's wonderful. You'll notice that I'm getting the next local virtual register, which might seem weird if your intuition is that returns happen at the end of a function lifetime. But consider if you want to return inside of an if statement or inside of an else or a while or something. Return statements do expect in LLVM, they do expect to consume a virtual register index. However, you can't assign them to a virtual register. So I can't say %5 equals ret void. That's not valid LLVM. It'll give me an error for that. But we do just want to get that next virtual register anyways, because otherwise Clang will give us a misnumbering error. So that's that. One thing that I will mention is I've updated the function post-amble quite a bit. Type checking, don't worry about it. You'll notice that I'm unconditionally generating a return statement at the end. This is completely valid, and it saves for the case. It saves the case where a programmer forgot to write a return statement. So if I've got function main return semicolon, or void main return semicolon, that is valid C. It works. But what if I just have void main open close braces? There's no return statement. I think most compilers would at least generate a warning and then generate the return statement for you. We are just going to unconditionally add a return statement because there's nothing invalid about saying ret void. Having two in a row. There's nothing wrong with that. It looks a little silly when you look at the LLVM, but it's a nice little easy fix for what could otherwise be a problem if we wanted to check. If we wanted to check that users had not written a return statement, that would be pretty difficult. So we are just going to handle that for them. So the function call code generation, LLVM call function, we can see that it gets called right underneath the return case. Nothing special there. And let's look at the function guts. So type checking, don't worry about it. I've got this call type. So if we've got a ret void, we don't need to, if we're calling a void function, we don't need to assign its output to anything because it doesn't have any output and it's not going to consume a virtual register. But if it's not a void type, then it is going to consume a virtual register. We do want to assign it. So that's what we're doing here. If we don't have a void function return type when we're calling a function, we're going to create a new LLVM value. This is going to be what contains the contents of the output of the function. It's going to be the next virtual register. It's going to have a number type that matches with the return type of the function. And then we are going to write out percent register number equals, and for the moment our generation stops. We are going to update this call type variable that I've got right here. Instead of void, it's going to now be I32 or I8 or something. And then we're going to add out to the list of loaded registers because we know it's just given that the return values of functions are going to be loaded. And then finally, we are going to write out call. We're going to give it the call type. And then we are going to say that that right now there's no parameters, so there's no parameter types. And then we're going to give it the function name. And we're going to get an empty list of parameters, and then bam, we return out, and ta-da, we've generated code for calling functions. Not too complicated. So there are some bug fixes that I've added in this update. So one big one is add loaded register. So you'll notice previously that I explicitly called LLVM load registers that append. and I would import LLVM loaded registers up at the top of the LLVM file right here. And this worked. The reason it worked is because all of the manipulation of LLVM loaded registers was done within LLVM.py, and that's fine. However, now we've got an extra bit of control flow outside of LLVM.py that does mess with the loaded registers list. Remember that when we start a new function, we want to say that our list of loaded registers is empty now. So, because there's that extra bit of control flow outside of the file, this import statement is not going to pick up those changes that happen in translate.py unless you re-import LLVM loaded registers every single time you use it, which is very tedious. So instead, I define this function add loaded register, and it's going to import our LLVM loaded registers. This is inside of translate.py, so it's not importing, it's just using the global LLVM loaded registers variable. And then we are going to append this register that we pass into it. So nothing crazy there. And then occasionally I'll need to do to get whatever I just added to the loaded registers list. So that just fixes that issue of not detecting changes that happen outside of the file. The next one, so in determine binary expression stack allocation, in the last branch I had forgotten to add a traversal of the middle child of our AST nodes. And because of this, if you had an if-else statement and you tried to define a variable inside of the else, or you tried to use a constant or something, that wouldn't work. You would never generate any free registers for it, and as a result, you get a bunch of bugs when you try to compile with Clang. And so now we've just added a recursive call down the middle child, and we've added it to our output list here. So thankfully, that was a very small change. And finally, just in this LLVM representation function for the type class, I added in just an extra case just to make sure that if you've got a function, you're always returning some manipulation of the return type. You should convert it from a token type into a number type as long as it's not a void. And finally, I have added in a factorial test. So those bug fixes made me realize that I should probably have some more complex functions to test with. So this is a non-recursive factorial function. You just plug in whatever you want to take factorial of into x right here, and it will return it down here. And you can see here we're calling Fred, so this print statement should print out 120. And so let me show that to y'all. We're going to do cat examples factorial. So this is what I just showed you, nothing crazy. We're going to do scripts run examples factorial, and we can look at the factorial function or factorial file. So we've defined Fred up here, and we're doing all this math, and we've got branch statements, and we've got unconditional branch statements, and here's our double return that I mentioned before. So it's very cool to see all this come together into a complex program, right? And then we're going to call Fred, we're going to store it in register 2, and we're going to pass that right into printf right here. So let's look at Clang examples factorial. We're going to spit it out into factorial 5. Oh, sorry, I was trying to compile a binary that I already made. Sorry, let me just rm factorial anything scripts run examples factorial. That gives us factorial.l, okay. clang factorial.ll minus o factorial 5. Okay. Let's call factorial 5. Oh, sorry. I had modified the factorial function to take in 15. Let's do all that one more time. Sorry about that, folks. 120. And yeah, I mean, let's change that to I'm gonna say 9. Oh, sorry, that should be factorial 9. And then let's call factorial 9. I think I'm getting my LVM files mixed up again. Vim examples factorial. We've got 9 scripts run examples factorial. Clang factorial.ll minus o factorial 9. Factorial 9. There we go. And just to check our work, let's define a factorial function in Python. So let's say if n is less than or equal to 0, return 1, return n times factorial n minus 1. Ta-da! Python agrees with our program, so that's very, very cool. And then the last thing I want to go over today is the optional homework. So this week's optional homework is one of my favorite features that I added to Purple, and that is n-base integer literals. So in most large languages, you can define literals in base 10, so that's like standard, 0 through 9. You can go in base 16, which gets you 0 through 9 plus A, B, C, D, E, also known as hexadecimal. You've got base 2 or binary, where you've got 1s and 0s. And you've got base 8 or octal, and you've got 0 through 7 on that one. So in Purple, I added the ability to define n-base literals for n is less than or equal to 36. So the way you do that is you type out your number literal, you add a hash symbol, and then you have a single character after that, either 1 through 9 or A through Z, and that single character defines the base. So for example, you've got LMNOP base R, that's base 27, and it gives you this big number in base 10. So it's not a standard C feature, and if you do it, then your programs that use it for your compiler won't work in other C compilers. But I think it's fun, and it's a nice challenging parsing problem. The reason for that is, well, your alphabet that was previously just for identifiers is now also used for integer literals. So it's a bit of a challenge, but it's not undoable. It'll take some work, but it's a lot of fun. This is an example program in Purple of what that looks like. So standard base 2, these are the same thing right here. But then you've got your G base, and that's some big crazy number, and you can also use lower cases, and here's some hexadecimal. And so anyways, that's all I've got for you. Thank you for listening, and hope you have a good day.